Good afternoon. I'm going to be talking about sharing lessons from a decade of development at Nine Elms. And I'm hoping the slides will go forward. Hello. The slides are not moving at the moment. There we go. Right, thank you very much. If you haven't heard of Nine Elms before, here it is on this map, the little star in the middle there. It's a small area of southwest London that historically has actually been quite quiet. The area of Nine Elms was quite... I'm sorry, I'm just going to ask if there's a problem here, whether the slides are going forward or not. Okay, thank you. They now are. This is a picture of Nine Elms in South London, just to the west of Vauxhall in 2010. The area was very quiet in those days. The only thing that was really happening in those days was there's an old power station called Battersea Power Station, and the centre of Nine Elms was covered largely with the old Covent Garden market, which had been exported from central London in the 1970s. What happened in 2010 was a very exciting opportunity for the US Embassy. They decided to move the US Embassy out to Nine Elms, and pretty much at the same time it was decided that Battersea Power Station should be redeveloped and the whole area around it should be redeveloped as well. And what previously was really quite quiet backwater of London suddenly turned into some of the most expensive real estate in London. So over 10 years, we've had quite a large change in what's happened. So I'm hoping the slide's going to go forward. There we go. That's what it's like now. These are both Google images. A dramatic change in the amount of development of high-rise development and low-rise development. The Northern Line extension has been built. Half of Battersea Power Station has been redeveloped completely, and it's an entirely different place, in fact. And we've had a lot of ground investigation information come out of that. As well as a lot of experience. If we look at the normal stratigraphy of London, we do actually have areas of Nine Elms which actually do have normal stratigraphy. Normally in the area we have about 2 meters thickness of alluvium, then we have a few meters of river terrace deposits, maybe 2 to 4 meters. We have about 25 meters of London clay, 18 meters of Lambeth group, 8 meters of Thanet formation, and some chalk underneath. This is totally normal for London. There are things that are slightly different. This area, you often have hydrostatic groundwater pressures. And the reason for that is something that was raised in a paper written in 1979 by a guy called Frank Berry. We also know that from work that's been done in the last 10 to 15 years, that the ground in London is not as layer cake as we thought it was previously. I'm not getting any help here from the slides moving forwards. And can somebody move the slide forward? Thank you very much. I think I'm going to do this verbally. In the last 15 to 20 years in London, we've realised that faulting in central London is actually common and often quite complex. And we've seen that particularly in Tideway and in the Crossrail ground investigation. Next slide, please. Can somebody move the slide on forward, please? Thank you. Okay, in 1979, 40 years ago, Frank Berry wrote his first paper about 26 what he called rockhead depressions in central London. What these basically features were basically that. In the London clay, there were depressions, some of them quite deep. And he noticed that these features were prevalent in London. So he's described 26 of them. We now call these things driftfield hollows in normal modern parlance. And he also noticed there was a whole cluster of them in the Nine Elms area where we got the red circle. If we look at this a bit closer, and this is a figure from a paper I should be mentioning, you can see these areas in the Nine Elms areas which are showing which ones were described by Berry. Okay. In his original paper, Berry described 26 driftfield hollows in central London. In the last 10 years, we've, as a team, discovered 80 in the wider area of London, more than 80 in fact. We're still finding them. So they're not just in central London, they are actually in a wider area you can see on this map. And we're still getting increased numbers being reported and discovered as people do ground investigation, and particularly in the Nine Elms area. Up till this year, there was no paper to actually update Berry's paper. And so you can see the link at the bottom shows this paper, which has just been published in the last week, or it's been put online. The URL should take you to that slide, to that paper, rather. If you wish to find it, I'm going to put some references up at the end of the lecture. Okay, next slide. There we go. If we look at the Nine Elms area in more detail, you can see these very large red or black dots. And the reason for they are so large is because although we get site information from a specific site, often the sites are very small and they don't actually delineate the entire size of the feature. Therefore, we have large dots. The red dots show where disturbed features are, and the black dots show where undisturbed features are. And I will go into detail about that. Obviously, these things don't always occur as large as this in real life. This is not the end information about Nine Elms. We are finding out from virtually on a weekly or monthly basis about new features in the Nine Elms area and in other parts of London. And a caveat, of course, about maps. There's a heavy data bias towards built-up areas and large projects. These features are greatly underreported. We're not quite sure exactly why this is, but it's often about claims after a project, about security, and sometimes it seems to be about embarrassment of not having done the right thing. The absence of data does not equal an absence of driftfield hollows, so we do have to be always aware of that. And even when we have found them, very few of them have been investigated fully. The vast majority of ground investigations are actually only shallow and only to the base of gravels. So what are driftfield hollows, if you haven't heard of them already? They are also known as buried hollows, scour hollows, pingos, rockhead depressions. We tried to get away from some of these terms because they're interpretative. They try and say how these things were formed. So driftfield hollows is the modern term. They're present near surface as localized, unusual thicknesses of river terrace deposits, or alluvium, or both. They can be anything from 5 meters deep to 90 meters deep, and they can be anything from 30 meters across to 500 meters across. And the important thing about them is they're not evident from surface features. They can be any shape probably, but they can also be linear or subcircular. And we believe they formed about 100,000 years or so ago, certainly from the information that we do have, fossil information. And this would mean that they were formed sometime during the end of an Quaternary ice age. Okay. One of the problems about driftfield hollows is a perceptual problem. Most people think of a driftfield hollow as being a relatively shallow feature, which has got localized thick gravel above it, and which has got perfectly normal ground beneath it. And we actually do have a lot of those in London, and they are possibly formed by erosion during the release of large amounts of water during the end of an ice age. These smaller ones tend to be the more undisturbed features which involve less ground risk. However, not all of these features are just a hole in the ground full of gravel. Sediment below the gravels and the alluvium range between normal looking river terrace deposits, in other words, intact, undisturbed materials. But we also have in some of these features this highly disturbed and intermixed material called melange, and we don't actually know what percentage have ground damage beneath them. So this is very important in terms of risk management. The larger disturbed or diapiric driftfield hollows basically have a larger area, obviously, greater depth. They often have unusual uplift of strata. So, for example, in this diagram, we've got the Lambeth Group and the Thanet Formation being uplifted towards the centre of the feature. And they can have intact, but they often have highly damaged or disturbed soils in them. They often also have fissuring and damage in the surrounding ground as well. So it's important to understand what your little bit of sand and gravel might turn into. One of the main problems about driftfield hollows in risk engineering is lack of experience. They are extremely rare, except in places like Nine Elms. Very little testing data is available, and this perpetuates the simplistic model, and it commonly leads to an inadequate site investigation. Often with the wrong techniques, not enough boreholes, insufficient depth, and poor logging practices. So summarising small, undisturbed driftfield hollows and large driftfield hollows. The small ones tend to be steep-sided depressions in the top of the London clay, yes, shallow, gravel-filled or sand-filled, and they can be linear or they can be a large area of random depressions and variable depth to London clay. The large ones tend to be steep-sided as well, up to 500 metres wide, up to 90 metres deep. They may have a thick layer of alluvium over the top of them. They have very thick gravels in them. They have unusual uplift, commonly intact to highly damaged soils beneath the gravels, and fissuring and damaging in the surrounding ground. The hazards that are related to this obviously are proportional to the sensitivity of the project. It's really important, of course, to think about these risks in any type of project, but clearly the larger the building, the more load is involved, the more complex the design of a project, the more the risks are going to be magnified in some respects. But it's important to look at the basic issues here. In undisturbed small driftfield hollows, variation in depth to intact strata is important. Pile collapses are quite common in the gravel layer. Pile tests failures can occur. You get lower bearing capacities and sharp frictions. One of the big things that we emphasize is the fact that there's potential risks to third-party assets, which are actually built within these layers of deeper gravels and alluviums. And we've made a real issue of careful monitoring. Careful monitoring of these third-party assets is really important, whether we're talking about the simple, less disturbed types of driftfield hollows and or the larger ones, especially with older pipes and tunnels. So monitoring, very important, but even more so when we get into the large features where we have great variation in depth to intact strata. Again, pile collapses, pile test failures. More importantly, when we get to these deep features, we can have deep and complex groundwater, and we need to manage that. We need to manage cut-offs and D-walls. There may, in some cases, be natural settlement, which is an ongoing historical feature, and that was certainly what happened to the driftfield hollow in the Olympic Park. And the very deep boreholes which affect the chalk as well may be a conduit for pollution, and they may equally be in hydraulic continuity with other driftfield hollows, as strange as that may seem. And that's from experience with the Lee Tunnel driftfield hollow. I'm going to be putting up some references at the end of this, if anybody would like to see these other papers. So we have some examples here of the type of materials. I'm just going to very quickly whisk through this. This is some of the deep alluvium we saw at the top of the driftfield hollow on the Lee Tunnel, which was intervened by a tunnel boring machine. We had up to 14 metres of alluvium there. Next slide goes on to river terrace deposits. We can have mixtures of sands and gravels, any kind of mixture of any of them, sometimes intermixed with London clay. The next slide is highly damaged London clay that we found in 19 Elms. As you can see, the actual texture of the London clay has really been mashed up, to be quite frank. It looks like it's gone into a food mixer. And even saying this, it's very difficult to actually describe what the damage entails unless you are very experienced in understanding what normal London clay looks like. The next slide shows a proper melange, a mixture of river terrace deposits and London clay together. The sandy material, as you can see, is it's kind of punched into the fabric of the London clay in this particular image. And then the next one is a melange of Lambeth Group and Harwich Formation and river terrace deposits, all completely messed up. Finally, we go on to Thanet sand and chalk melanges, and these have both been taken from East London. This is one from the Olympic Park, driftfield hollow, and the next one is from the Lee Tunnel. Fortunately, so far, we haven't found any very deep driftfield hollows in the Nine Elms area. So if we go on to some information about ground investigation. The site investigation of driftfield hollows is quite complicated because the techniques that we have available are limited. Excuse me, I'm just going to get back. Okay, common investigative techniques we use are cable percussive boreholes, rotary, sonic, and CPTs, cone penetrometer. The cable percussive ground investigation through thick gravels can be absolutely painful. The main problem is that actually we're not recovering any of the fines in the PSD samples that we take from cable percussion boreholes. And if we are actually trying to design any kind of grouting, which may be required for, say, for example, for tunnelling, that could be lost information. Rotary cord boreholes can give you good recovery in the soils that recovered beneath driftfield hollows or in driftfield hollows, but they give you basically poor to zero recovery in the terrace deposits. Again, we may need that information for grouting. Sonic boreholes, rotosonic boreholes, generally give you good recovery in all of the sediments, but the clays may come out as slightly stiffer than they should be, and the chalk, if you're intervening into the chalk, drilling into the chalk, may be much weaker than normal. And of course, both of these affect lab testing results. And then finally, CPTs, which we used on a couple of projects in the Nine Elms area. You have to actually drill through any kind of gravels before you start using it. And of course, gravels can be quite common within melanges, the mixtures of river terrace deposits that we find in these deeper features. And this may distort results and giving interpretation which is quite difficult to interpret. The less data we get eventually is the more misleading the model we get. Can you have the next slide, please? Okay, next. Thank you. Modelling of driftfield hollows can be done in a number of ways, but we've used Surfer quite commonly. And if you have less data, you end up with a kind of smoothed bullseye, which may generate misleading depths. Therefore, your actual output is only as good as the number and quality of boreholes, and only as good as the quality of the logging that's been done in the first place. And in this image at the bottom, thank you, we can see an early stage of the interpretation at number 1 Nine Elms, for example, where it appears that we've only got a depth of 14 meters of gravels in the bottom right hand corner of the image. If we look at the second image, which has more boreholes interpreted, you can see that there's a quite dramatic difference in the second slide, where we can see up to minus 24 as the base. This is on the top of the London clay here. So the amount of data and the quality of the data has dramatically changed how accurate a model we've got. So in terms of ground investigation, what is actually needed in terms of driftfield hollows? At the very least, even for a simple undisturbed driftfield hollow, we need to investigate the morphology in terms of pile design or any other kind of foundation design. So it requires more ground investigation boreholes than normal. Boreholes should also be through the base of the gravels into the underlying sediment so that we know whether it's been damaged or indeed if it's London clay at all. And they should be logged by an experienced logger. And for the larger features, we need a lot more information. We need to understand not only the degree of morphology change from normal, we need to know the degree of ground damage that may be happening in the feature. We need to understand about porosity and permeability. We need to know if the chalk has been involved. We need to know if there are environmental issues in terms of leakage to the chalk aquifer. We need to know about the groundwater for cut-off design, and therefore we need to drill deeper than we would normally think. We need to have boreholes which are well logged, and we need to realise that you can lose a driftfield hollow easily between 100 metre centre boreholes. Just a couple of quick slides I'm going to do now, two from number 1 Nine Elms. Hello. Sorry about the problems with the slides here. Thank you. Okay, this is one of the multiple sections that we generated across the site, giving a 2D interpretation of what the ground was like. It was incredibly helpful because of the complexity of the 1 Nine Elms project. And it actually enabled really hard-hitting decision as to whether there could be a tunnel between the two parts of the buildings. What we can see here is we've managed to get not only the increasing amount of gravel, depth of gravel on the right hand side of this cross section, but also quite a lot of detail about the different types of melange and the properties of this mixed up material all the way across the site. Next slide, please. And this led us to be able to make 3D modelling of the entire site, including the different types of melange. So we've learned an awful lot. And the conclusions, there are many conclusions. Driftfield hollows can be small, undisturbed and relatively simple, or large and complex and disturbed, and sometimes maybe something in between. Risks, of course, are proportionate to the type of driftfield hollow and the sensitivity of the project. Large driftfield hollows can be completely missed between boreholes with apparently normal levels on either side of them in the stratigraphy. And geology is often very complex within the features, and it requires the best type of ground investigation. Reporting driftfield hollows in ground investigations is still low, even in areas like Nine Elms, where actually they are relatively common. Large driftfield hollows have adversely affected the ground at greater depths than we previously thought, and even well-controlled encounters with a driftfield hollow at depth, for example with a TBM, can lead to settlement at ground level. And large driftfield hollows reaching the chalk may be in hydraulic communication with over considerable distances with other driftfield hollows. So it's important to always get the right advice, the best advice, and to ensure good communication, ground modelling and planning for a satisfactory outcome. Thank you.